Hi everyone, my name is Jay Metz. I am a research and development engineer for Cisco, but today I'm going to be talking to you on behalf of the board of directors for SNIA, the Storage Networking Industry Association. Today's talk, we're going to be focusing specifically on the fabrics part of NVMe over fabrics. Now, we're not going to be doing this just in isolation. Obviously, you can't talk about NVMe over fabrics without talking about NVMe. So we'll do a little bit of backtracking and try to get people up to speed. Just as a little bit of a credibility, I am on the board of directors for SNIA, which is one of the reasons why I was asked to come and talk to you on behalf of SNIA. I'm also on the board of directors for the NVM Express group, and I'm on the board of directors for FCIA. We're going to be touching on all of these different elements. What's that?
Busy man, aren't you?
I am a very busy man. And believe it or not, the board stuff is not even my day job. So it's kind of interesting. The reason why I point this out is because all of these things are related to everything else. The stuff that goes on inside of NVMe, NVM Express Group is going on inside of SNIA, which touches the stuff that goes on inside of Fibre channel, and so on, and so on, and so on. So to that end, what I'm going to try to do today is give you a little bit of a refresher for what NVMe is, talk about what NVMe over fabrics is, and then we're going to focus specifically on the fabrics part itself. Now, believe it or not, this is going to be something of a pretty deep dive for some. It's going to be kind of routine for others. I'm going to try and see if I can stretch and straddle that kind of gap. Before we get started, I want to do a couple special thanks. Obviously, nobody does anything in isolation, and all the work that you're going to be seeing here, it's come from, in some fashion, through contributions of other members of the NVM Express group, as well as SNIA and Fibre channel. Okay, so I wanted to give a special thanks to the people who have contributed in some fashion to this particular presentation. Okay. Let's talk about NVMe, and what is NVMe? Okay, first of all, NVMe is an organization, and it's a technology. It's the organization that creates the technology. So when I say NVMe, I will talk about the technology. When I say NVM Express, I'm usually referring to the organization, okay? And so NVMe itself is typically a PCIe-based approach to doing storage. NVMe over fabrics is when you do a remote access to an NVMe device. So that's basically the kind of terminology that I'll be using in this particular presentation. The NVM Express group works in three different specification types in particular. The first one is what's called the NVMe base specification, which typically works for PCIe, specifically designed for PCIe. If you want to have remote access to the drives, we call that NVMe over fabrics. And fabrics is supposed to be a transport-agnostic system of moving data and NVMe commands from one point to another. The agnostic part is really important because of the fact that when you do that, you have to make some slight changes inside of the NVMe base spec to be able to do that. The third aspect, which unfortunately we're not going to be able to have enough time to go over today, is the NVMe management interface specification. Now, the management interface specification talks about everything from the in-band, out-of-band control plane to the actual chassis management to the PCIe bus management. It covers a large number of areas that unfortunately we just don't have the time to go over today.
Where's the NVMe namespace kind of stuff going?
NVMe namespace fits into the base specification. And it's a good question because we're going to be talking about that in about 3 seconds. But you're right. I mean, so I have a feeling what I'm getting is that there's a couple names that, shut up, Howard. There are a couple names I think that you probably have heard about. I'm going to try to put the glue together and make sure that you can figure out the overall ecosystem of how this stuff works. And I have a lot of pretty pictures to help figure out where things are going to be put together. Okay, so what is NVMe? Well, realistically, when we start talking about NVMe, what we're looking to do is compare it to what the alternatives are. NVMe is a command set structure and a way of communicating between a host and a corresponding device. Up until now, that device has been SCSI. Right? When we do SCSI, we have effectively a relationship between a CPU, also we can call it a host for our purposes here, and a corresponding device. And SCSI is ubiquitous. We can do it with tape devices, we can talk to drives, SSDs, we can talk to scanners, we can talk to all kinds of stuff. It's a great protocol for being able to communicate with devices. Flash, though, and other non-volatile memory types do not necessarily have the same needs as a SCSI device does. So as we start to reduce the latency requirements inside of a flash device, now it used to be 8 milliseconds for a spinning disk, now we're getting into the 100 milliseconds or, 100 microseconds or sub 10 microsecond levels. These kinds of relationships between hosts and targets are all obviously going to change, right? And as a result, when we get closer and closer and closer to memory speeds, right? Now we're getting to be less than an order of magnitude away from memory speeds, which means that if we can do that, maybe we can start treating our storage like memory and our memory like storage. That's effectively the metaphor that we're looking to use, and it's for those of you who are starting off with the NVMe stuff, it's a good way to start thinking about things. It's a little bit impractical when you start pushing the metaphor a bit, but for right now, think of what NVM does is treating the storage and memory as kind of the same thing. When you do that, you get some interesting things. For instance, in a SCSI environment, the CPU does not speak natively to the storage device. You have to go through an adapter to do this. It usually is a SCSI adapter, a SAS adapter, SATA adapter, whatever it is. You have to be able to translate those commands from a CPU into the actual corresponding device. When we start using an NVMe approach, however, we are using the same language that the CPU uses, which happens to be PCIe. CPUs do talk natively to PCIe, which means that if we put storage onto a PCIe bus, we can use the PCIe semantics to address and use non-volatile memory the same way that we would normally use in any kind of PCIe command structure. The semantics are the same. So what happens is we are able to use the parallelism and the low latency of an SSD in a memory kind of a metaphor, or approaching a memory metaphor. And that's where NVMe really starts to shine. We get even better when we start to look at how we communicate between the two devices. Now, when we talk about NVM Express, it's a little bit different than what we do with SCSI, because basically the SCSI bus is really kind of an airlock system, right? You have your CPU, you talk to an adapter, the adapter changes it into the proper command set. The proper command set then gets sent onto another wire, and then that another wire has to be translated, and then it gets off into a network, and each one of these airlocks can prevent the relationship from being completed natively. Okay? What NVMe does, though, is it creates a relationship between the actual storage target, in this particular case is identified as an NVMe controller, and the actual host itself. And we do that by establishing what are called Q pairs. Now those Q pairs, there's three basic types of Q pairs. Well, there's really two, and then that one of them has it's split into two different parts. First of all, you have what's called an admin Q pair. And those admin Q pairs, they all have the submission queue and the completion queue. That's ubiquitous across all the different types of Q pairs. Admin queue does essentially what you think it is. It's the control plane for the relationship between a host and its corresponding target. Then you have what are called the I/O Q pairs. Right? So you can have the I/O Q pairs for submission and completion. And the interesting thing is that because of the fact that we now have a sense of parallelism, I can have multiple submission queues to a single Q pair. And we've mapped these to CPU cores. This is completely different than what we currently do with a SCSI-based environment, right? What we traditionally do with a SCSI-based environment. In other words, basically the CPU has to talk to an adapter in a SCSI-based environment. And here, the CPU is talking directly to a controller based upon whatever queue we're mapping the Q pairs to. This is the parallelism that we're talking about. And what winds up happening is that I can actually drive multiple relationships within a single CPU to multiple different targets. Those targets do not necessarily have to be on the same system. They don't have to be local. Okay? So if you take a look at this, this is a logical diagram of the relationship between the end devices. What happens in between can be varied, and it will be varied, and that's where some of the confusion can come into play. Okay, so that's why it's very important that we understand that this relationship exists no matter what we're talking about.
Okay, but that relationship between cores and queues is common practice, not required, right?
No, it's required. It's part of how NVMe creates a relationship. The reason why we do that, as a matter of fact, is that you can actually you want to be able to do this so that you can have source core interrupt steering. So, for example, if you've got core 0 getting a completion queue back, you do not want to interrupt core 1. So you will pin the different submission queues and
right, but I may want to be managing more queues than I have cores.
Right.
So it's not a strict one-to-one relationship.
No, you can actually do a couple different things that are pretty granular. You can create, for example, in this one you can see you have multiple submission queues to a particular core.
Yeah.
Right. And you'd have one completion queue that was where the interrupt steering would go to and would interrupt that particular core. You can have multiple submission queues in a particular core. Now, the difference here is that this is true for PCIe, but not for NVMe over fabrics. In NVMe over fabrics, it is pinned to a particular core. You only have a one-to-one mapping with NVMe over fabrics. We'll get to that in a second, though.
It's core, it's not processor.
That's right. So if you had a 1,000 core processor, you could conceivably put in 1,000, Q pairs. Yep. But the idea here is that
it's Q pairs, but it's actually could be more than two.
I'm sorry?
You mentioned it's a Q pair, but it's actually more than two in some of these cases. Multiple submission queues can exist.
Right. Well, actually, no. Technically, each submission queue has a paired completion queue. So that is a pair.
Not what you showed on the prior chart.
Hang on. This submission queue is paired with this completion queue. But this submission queue is also paired to this one. There's basically two pairs. It just happens to be that the completion queue is shared.
So why do you have multiple submission queues?
Well, there's a number of different ways that you could probably do that. There are some. Part of it has to do with where you want the subsystems to exist. So, for example, if you happen to have a daughter card, for example, with multiple subsystems inside, you may want to be able to attach your individual Q pairs to multiple different subsystems inside of a PCIe environment, right? So what will end up happening is you have the flexibility of physical form factors that would then be able to be managed independently, so that you're not basically having to stripe across all different 4 subsystems at the same time. Okay. But the idea here is that we want to be able to, the ultimate idea is that we want to be able to have this kind of lateral approach to being able to handle whatever physical form factors there are, and a vertical form factor for being able to stretch out across multiple distances regardless of the transport type. So this kind of lateral and vertical approach is very flexible because these are really logical progressions. They can be done in hardware, they can be done in software. Most of the time they're done in hardware. Okay, so let's dig a little bit deeper into what these things actually mean. Each of these commands are put into what's called a queue entry. Now, obviously, the host has to put in a submission entry into a submission queue entry, and it goes into the submission queue. Makes sense, yeah? Okay. Same thing on the way back. You have a completion queue. It goes into a completion queue entry. Now, this becomes a drinking game very quickly, so you have to bear with me. But the idea here is that when you have the connection already established, which is what the admin queue does, an admin queue will set up the establishment of the relationship between the corresponding queue pairs and the target. Then the submission queue and the completion queue are created. And the idea is that you basically take the submission queue entry and put it into the submission queue to be sent over to the target. And we're going to get to the mechanics of this in just a second. The reason why I want to point this out here is because we're going to use this a lot, right? So these graphics here that you see right here, and we're going to be seeing these a lot. Okay? But the idea is that this is an entry point that goes into a specific ring buffer that can handle up to 64,000 of these suckers. Okay? There's a lot of submission queue entries that you can put into these things.
Okay, and buffer address there is a pointer to a memory location?
It can be, yeah. In fact, we're going to get to that a little bit later on as well.
Okay.
It turns out that there's a little bit of a difference as to the way that you can actually approach this in the fabrics. But generally speaking, yeah. Okay, so what winds up happening, this is a logical model for how these things actually work. And so bear with me because I don't want to confuse you, but this logical model works exactly for the way, this way for PCIe as it does for fabrics. The mechanisms will change a little bit, but the same process happens no matter what. The host driver, the NVMe driver, will place a submission queue entry into the submission queue, which is then processed by the NVMe controller, When the command is completed, whether or not data is required to be transported or not, then the NVMe controller goes back the other way and puts a completion queue into the completion queue entry into the completion queue, at which point in time the NVMe host driver decapsulates or de-enqueues rather the completion queue entry, and then a pointer is set up to the original submission queue to free up to put in another command. So far, so good? Mm-hmm. Very, very strict, basic. There's really nothing magical.
These are in the memory of the host system, and the device that's local and or remote is looking into the memory of the host system to process these SQEs.
So hold that thought, because we're gonna go into that specific detail.
That thought.
Yeah. I'm talking about the generic model here. I'm going to be digging deeper into it.
All right.
And you can tell he's getting impatient. Show me. Okay, so this is, I didn't want to answer that on the generic model because the way it works between PCIe and the way that works for RDMA and Fibre channel are different.
Yeah.
Okay. So what happens in PCIe?
I thought one thing, though, that the command could include the actual data. For like a write command, you could actually incorporate up to 4 kilobytes of data with the queue entry. I don't see that in your queue entry, so.
That's because I haven't gotten there yet.
We haven't talked about data payload.
I did ask you to hang on.
Yeah.
Okay.
Because what you're talking about is an in-capsule message transport, which is used for fabrics. We're still on PCIe. So we'll get there, I promise.
All right.
Because we have to go through this first in order to get to that and understand why.
Okay.
All right, so what happens here is that the host driver is going to enqueue the submission queue entry into the host resident memory. Now remember, we're talking about having the CPU treat the storage as memory and vice versa, okay? And this is going to be a theme that's going to come back over and over again. Effectively, what happens is the host driver notifies the controller about a new submission queue entry by writing to the doorbell register at the NVMe controller. In other words, it goes ding, order up. What then happens is that the NVMe controller sends back the command. In this particular case, it's a PCIe read, which effectively goes and retrieves the submission queue entry out of the submission queue and then writes it back into its own memory buffer. So far, so good? Now, if there's any data to be transported at this point in time between the controller and the host, this is where it happens. Doesn't have to. You don't have to have data transport, but it could.
Well, it is storage. It's kind of the main thing we want to do.
Sorry?
It is storage, putting data in, pulling data out. It's mostly what we want to do.
True, but if you're doing a flush, for example, it's a different kind of thing. Okay. So then what happens is once the actual processing is done, the NVMe controller then enqueues the completion queue entry into the completion queue and sends it back to the host driver, at which point in time the host driver will dequeue the completion queue entry and update the head pointer for the submission queue. Okay. Again, same thing. This is just how the PCIe does it. Now let's go talk about the NVMe over fabrics, which is where Ray is chomping at the bit to learn about. Okay.
Maybe.
The same exact model happens inside of transport. Now some of the mechanisms will change, but ultimately, what we're doing now is we're inserting a different type of transport mechanism inside. The key thing here, however, is that there are certain types of characteristics inside of Rocky, iWarp, InfiniBand, and Fibre channel that have to modify that intersection between the actual host and the target. Okay. Nevertheless, the same things are exactly the same. You still have the admin queue, you still have the IO queues, you still have the submission and completion queues, you still have the host drivers, and you still have the NVMe controller. Now, one of the things that I didn't have the slide in here, and I said that I might not have it, but to your point about the namespace IDs, okay, because I want to get to this point now because it may come in a little bit later on. The anatomy of an NVMe device is called an NVM subsystem, okay, non-volatile media subsystem. And so what happens is you've got your basic flash memory. On top of your flash memory, you have the ability to logically construct an LBA addressing system. That LBA addressing system is commonly known as a namespace inside of the NVMe parlance. The NVMe namespace is controlled by the NVMe controller. You can have as many namespaces as you want for an NVMe controller. They're assigned an ID. That ID is then sent back up to the host where it is identified as the LBA address to be sent to the actual memory space for that particular namespace. It's, in fact, I'll go back here. And I thought I had I skipped over it only because of the fact that I thought I had a graphic for it. But you'll notice, for instance, in the submission queue entry, you've got the command ID, you have the opcode, and this is the namespace ID. So every submission queue entry has its own namespace identifier to go to specifically where it's supposed to be happening. Each one of these header fields is used for error checking as well as security elements, and there's some placeholders for that in the future.
So queues aren't assigned to namespaces?
No.
Okay.
No, queue pairs are only assigned between the host and the actual NVMe controller, and it's up to the NVMe controller to process those entry points. So you can have, in fact, you will have multiple namespaces per NVMe controller, and this is how we identify which namespace it's supposed to be identified with, as well as the actual sequence ID for what actually gets, what command gets which. That's why these commands can be done out of order, for instance, because they're always associated with the sequence ID.
Why doesn't the completion queue entry have an end space ID as well?
Because it doesn't need it.
Back to the command ID.
You don't need it. All you're doing.
You say, give this to Ray, and then you get a response that says, here's the response, but.
But I could be Joe giving the response.
Yeah, but.
Or
command
But the
ID.
command ID,
Dr.
I
J.
remembered that I sent that command ID to, the driver has to remember that command ID X goes to
Is the canonical
namespace
reference.
Y.
Okay, I got you.
Okay, so what are the different types? When we start talking about the PCIe stuff, we're really talking about a memory mapped architecture where the data and the commands and responses are using the shared memory. Remember I said we're treating storage as memory at this point? Well, really within a PCIe environment, that's pretty natural. It's a shared map namespace, and a lot of the commands are really PCIe commands, right? So when you start to go over transport, things can change, right? You don't actually have a real physical shared memory. You can access remote memory, but you don't have the physical shared memory, but you have to behave as if it is. So that's where certain types of messages comes into play. So we call these things capsules, all right? And when we transport these capsules, we have a couple different metaphors. We have the memory, and we have the memory message. We have message, and we have message and memory. Sorry, ugh. Told you we're getting into drinking game territory here. And I'm going to go into some of the specifics here with regards to these things moving forward. But there are two basic types. First type is what we have, the data and command and responses are using the capsules for both. This is typical in Fibre channel. It's optional in TCP. And basically what it means is that instead of having to directly address inside of a memory space, you're taking the command and the data and you're popping it into a single capsule to be processed according to the transport mechanism for doing data and commands. Now, with message and memory, though, it's a little bit different because what happens is you will use the capsules for the commands and the responses, but the actual data transfer could be transport specific. For example, RDMA does something different when it handles data transport. And we'll talk about that in just a second. But before we do that, let's talk a little bit about what the differences are between NVMe and NVMe over fabrics. First of all, I already mentioned one of it, which is that you basically have a one-to-one mapping between the IO queues from a host to a corresponding target. And because of that, the controller is really only associated with one host at a time. Now, this may change in the future. These are not necessarily set in stone forever and ever, but as far as the base spec is concerned and the NVMe over Fabrics 1.0 spec is concerned, this is the way that everything is starting off, probably for simplicity's sake. Okay? NVMe over Fabrics doesn't define an interrupt mechanism that allows the controller to tell the host to update the submission queue. Now, the reason for this is because of the fact that you don't necessarily want your transport mechanism going up into the host driver to basically tell it to update the submission queue entry head pointer. You really want the host driver to do that on its own. So the transport mechanism doesn't do that. NVMe over Fabrics does not support physical region pages, but requires the use of scatter gather lists for admin. Now, the difference here is, are you familiar with what the difference is between physical region pages and scatter gather lists?
Not at all.
Okay. A physical region page is effectively part of the mapping that we're looking at for understanding where the memory space is. A scatter gather list is an address length tuple, which effectively allows you to say, I want to start from this point and go to this offset. And that is how Fabrics is able to find out not only the memory region that it has to read if it's an RDMA situation, or if you're looking for a location on a NAND flash, for instance, for using Fibre channel, whatever, you basically send out those scatter lists.
It's almost like CCW, old address pointers and stuff like that kind of stuff.
Exactly. So in fact, you can use SGLs for PCIe based, and I don't know for sure, but I do know that there are a couple of vendors who are at least exploring scatter gather list approaches inside of a PCIe memory space, because it's easier just to write to scatter gather lists and Fabrics either way. Now, ultimately, from the end user's perspective, as long as it works, it doesn't really matter. It's all about internal efficiencies, really. Okay.
Quick question for you. What's the driving use case that switches you from NVMe to NVMe over Fabrics?
The exact same use case that you went from direct attached storage to SANs. Scale.
Sharing.
Exactly. You just wind up with a limited amount of capacity that you can have in a single box. You don't necessarily want to be able to limit your access to NVM memory inside of a single box. You want to share multiple situations. You know, there's every reason that you can imagine for SAN versus DAS is the same one that you would do.
Which vendors are leading the charge with NVMe over Fabrics? Their solutions and are doing a good job of it.
Well, it's really difficult because
Systems makes a really nice NVMe over Fabrics target chip, as does Kazon.
Yep.
NetApp and Dell EMC have announced but not delivered NVMe over Fibre channel products, and Pure was kind of the first of the mainstream vendors to talk about NVMe over Fabrics, but
Pavilion
again,
Data uses
not shipping.
Pavilion
on the
Data
front
has
end.
their own kind of software associated TCP version of, as well as RDMA. There's a couple others out there, E8 and Accelero, that are playing
kind
the
of
game.
pre-standard. They're not really NVMe over Fabrics, but they are NVMe over Ethernet.
I think it typically doesn't talk vendors.
Well, no, and I won't. I mean, I can.
Which is why Ray and I just pitch in.
Oh, I appreciate that, but I will say that within the NVM Express group, it's not quite so straightforward, because the dependencies go beyond just the Fabric side, right? The dependencies go well into, like T11 is doing the NVMe over Fabrics for Fibre channel, right? And there's a good 50 companies in there, and then the NVM Express group is working on the bindings for RDMA and TCP, and there's 130 companies in there. The Linux drivers have to be updated. The VMware drivers have to be updated. The Microsoft drivers have to be updated. So it's not quite a straightforward answer as somebody creating an array that does it. You have to remember, this is an end-to-end thing.
And
There's a civil war going on between Rocky and iWarp. And how does SNIA talk that?
From SNIA's perspective, it's an option. And the idea is that every technology has a sweet spot for use cases. If Rocky fits that sweet spot for you, then that's great. If iWarp fits that sweet spot for you, that's also great. The real problem that people have is that neither iWarp nor Rocky have a long history of storage from the host. Right? There are places, there are arrays that have RDMA-based approaches, whether it be InfiniBand or Rocky or iWarp, inside of the actual box, but not from the host. So there's a lot of questions that are going on that need to be answered either way. And TCP is going to be the exact same thing. You know, there's a lot of work going on it. There's a lot of people who are proponents of it. But ultimately, you want to make sure that it solves a particular problem for you and doesn't introduce others. Okay. But to that point, I actually have the comparisons there, and given the time limit, I want to try to make sure I cover the highlights of these different points. I don't want to just skim through a whole bunch of slides, but there are some things that are going to answer some of those specific technical questions. Now, Ray, you asked me earlier about what happens with the host memory buffer and where the actual controllers are. There's two different types of data transfer. And you have what's called a controller-initiated command data transfer, and then you have an in-capsule data transfer. okay? The RDMA-based approaches and the PCIe-based approaches use this kind of approach. So what happens is that when you have a controller that initiates the read or write of a command, effectively you have to translate the copy, so to speak, of whatever it is from the host memory buffer into the controller memory buffer. Now the way that currently works is that you send off a command to the NVMe controller, and then the controller then sends a read command from the actual host. So that's an actual write. RDMA writes are in reverse, right? You send a command for the controller to read from your data set. That's how that works, all right? Now, you can do this inside of PCIe transport, you can do it inside of an RDMA transport, and it is required inside of a TCP, but you can also do what's called an In-Capsule transport. So let's talk about what the In-Capsule transport is. Instead of just sending out a command and then asking the controller to read the command out of the host memory buffer, you can send both the command and the data at the same time. You can do this inside of TCP, and this is how you would do it inside of Fibre Channel. Remember I said Fibre Channel has a different way of handling data transfers than RDMA? This is what we're talking about. Okay? What happens here is that the NVMe command and the command data are sent into the same capsule, and here's our friendly little submission queue entry with all the information that you need, but plus an additional packet
Payload
type for your data, and you can allow the actual transport to break up the amount of data that you need into its appropriate capsules, just like Fibre Channel does, just like TCP does.
It works well for writes, but how does read work in this scenario?
It's essentially the same thing. I mean, basically...
Completion level?
At the completion level, what do you mean?
So the completion queue entry has the data that's been read?
No, the completion queue entry is a completion of the command, right?
I'm doing a read. I want to do a complete.
Right. So we separate out the read of the data that gets transferred out, and then the completion queue entry is its own command, right? That's why the completion queue entry is such a smaller box on the graphic. The completion queue entry really only says we're done. That's really what it does.
There's something more in there. I've seen, and I think Accelero is a proponent of this, where they do some internet-level statusing that's able to be done on the completion queue entry that wasn't necessarily obvious.
No, I mean, and you're going to find that there are going to be some extra sauce for what a lot of the vendors will do. Right, because the way Accelero's model works, there are other things that they wish to do triggered based upon what the completion queue entry does. Right? They're not just updating it.
Yeah, but Accelero isn't really NVMe over Fabrics. It solves the same problem, but it's not.
Okay.
Right.
It's not the same implementation.
Well, it's not designed, it's not spec and then Accelero wrote their thing,
Yep.
spec was developed at the same time, so they're not congruent.
That's exactly right, and it's because of this. Right? So what makes fabrics fabrics are the bindings. Right? You can do this without having a standardized approach to doing NVMe over fabrics. And that's where things get a little confusing for people. The reason why I was telling you all of these different things in such a pedantic way is because of the fact that you can deviate from these things if you wish to do something special. Right? But what makes a standardized NVMe over fabrics is the bindings. If you apply the bindings that are set in the specification, then you are a standards compliant NVMe over fabrics approach.
So the objective for this point is to say, if you respect these standards, we can imagine interoperability in the future, as opposed to all the siloed products we have today, which is if you're E8, you're E8 top to bottom. You can't mix and match any of these other products.
That's right. Now E8 and Accelero and a bunch of the other startups have it said publicly that they're going to be doing NVMe over fabrics. Well, what does that mean? It means that they're going to be implementing these bindings. Okay? Right. And so that's the reason why I'm going here right now, is because how do you know if something is standardized or not? It's this. Okay? Yeah. This is the most important slide for NVMe over fabrics. Without question. It's the bindings that hold the glue between the NVMe spec above and whatever implementation is below. Okay? Now, what do the bindings do? Bindings basically define the relationships that exist between the host and the corresponding storage targets. Right? It identifies how the SGL descriptions are supposed to be configured. It identifies where data can be placed. It identifies what security requirements are going to be placed, right, and what types. And it also identifies the transport capabilities. So, for example, in an NVMe TCP, which I was telling you about before, are you going to be using in-capsule data transfer, or are you going to be using the the memory buffer side of things, right? That's very, very important. Okay, so really quickly, before we get too far, I'm not going to spend a lot of time on this one. Just keep in mind, but as you start to look at your fabrics, and this goes to the earlier question of how do you know which one to use, the important part here is that NVMe will blow away your performance metrics that you're used to, right? We can blow out drives, CPUs in a heartbeat with like 3 or 4 drives. Right? It's that kind of performance, right? So when we look at which kind of transport we're looking to do, we have to build the network according to whatever application that we're looking for. So applications that are being built for the Facebooks, Googles, which are the companies that are really heavily behind the NVMe TCP, for instance, they have different application requirements than, say, a general IT mission-critical system with multiple databases. So what's going to wind up happening is that the ability to configure networks properly will be dependent upon the application requirements, not necessarily just the actual storage types, okay? So it's not quite so simple as saying, well, I got, RDMA is Ethernet, for Rocky, and so is iWarp, and so is TCP. It's got to be all the same, right? I just put it in a network. No, not really. Okay. In the interest of time, I have 3. Let's see, I have 3 different approaches for fabrics, really quick. We have 5 minutes left. I have the Rocky iWarp conversation, I have the Fibre channel conversation, and I have the TCP conversation. We can either go really quickly through all 3, or I can go one in depth of 5. Do you have a preference?
All 3. All 3.
All 3, okay. So I apologize for any kind of speed run that we're about to do, all right? Basically, when we start talking about RDMA, what's the concept of RDMA? Remember, storage is being treated as memory, right? So RDMA makes sense, remote direct memory access. We take a bit in one and we use it at another, right? We access the memory remotely. Now this has been used for years for high performance computing. It's been doing a whole bunch of good stuff for being able to have in-memory locations, because then we understand this really well. So if we treat storage just like we treat memory, this should be a no-brainer. Well, it does. And what happens is you have to have what's called an RDMA capable NIC, or an RNIC. It's a specialized piece of hardware that sits in front of the CPU from the network that is able to translate the access requests into a remote call for some other memory space.
The good news is almost every 10 gig NIC is an RNIC. The bad news is some of them are one kind and some of them are the other.
That is true. Yeah. You cannot mix and match. That does not work. So basically what happens is that we want to try to be able to use the memory space. This is a kind of a fancy way of saying, I'm going to bypass the OS kernel and go straight into the memory space, and I'm going to use the RNIC to do it. Right? So I can avoid the need for handling any kind of processing inside of the CPU. This makes it very, very quick, and it also allows you a greater degree of flexibility of where the memory has to be located. Now, there are different ways of doing that, but from an NVMe perspective, what winds up happening is we are taking the queue pairs that we already know and love for NVMe, and we're associating them with the queue pairs that we already know and love for RDMA. We're daisy chaining the queue pairs. Right? From our submission queue entry point, we basically take the submission queue entry and we put it into a send queue for RDMA. And it goes through the RDMA process and it gets dequeued at the NVMe controller, because effectively the send queue of the RDMA NIC goes into the submission queue entry for the controller. We're just daisy chaining the queues at that point, which means that we can now extend and expand out without having to break any kind of the queue pair mechanisms. There's no muxing, there's no consolidation of that stuff. Now, I'm only showing the send part here, but the same process works for a completion queue entry going back the other way. Okay? Now, this is what it would look like inside of a local NVMe versus an RDMA fabric, right? Basically, you have your NVMe controller with your admin queue pairs and the different cores, and this is exactly the same. Why do I point this out again? Well, the idea here is that we don't want to break the multi-queue model, right? And we can do the exact same thing with any RDMA base, and this is true for InfiniBand, it's true for Rocky, it's true for iWarp. Okay, the idea is that we don't all of a sudden need to have additional CPU utilization because of the fact that now we've got the muxing here.
So Fibre channel actually doesn't use RDMA per se.
No. In fact, our Fibre channel uses a form of zero copy, but it's not RDMA direct. So both Fibre channel, in fact, we're here in Fibre channel right now. So really what's happening is we're taking the TCP upper layers and we're then mapping it into a Fibre channel, an NVMe approach. So the NVMe host driver then gets connected into a Fibre channel, what's called an information unit. So that hook is actually extremely simple. It's a very basic hook for getting Fibre channel into, or NVMe onto a Fibre channel link. So let's see. That mapping looks like this. So here you have your submission queue entry point, which gets put into a Fibre channel command IU. That command IU is then sent across the wire in the exact same way that you would send any other Fibre channel frames. And then it gets, the completion queue entry gets put into what's called a FCP response IU. And so just like we put them into send queues and receive queues in the RDMA, we're sending in a FCP IU for send and receive. Same basic principle. And TCP has the same concept. Okay, you have specific one-way concepts for communication. And this goes to the zero copy that you were talking about, Ray. Effectively what we're doing is we're DMAing the data and the commands directly into buffers that exist on either side of the HBA system, at which point in time it's then communicated into the host memory buffer queue on either side. And to the point, if you're really curious as to what it looks like, this is what NVMe over Fabric using Fibre channel looks like. You'll notice at the bottom you have the I/O read and the I/O write. Now, this is a comparison to an RDMA ladder diagram. It's exactly the same. There's no difference, right? So the idea here is the transport is truly agnostic. So what we do is we can take the actual advantages of any particular transport that we have in our environment, and then we can apply it that way. Last but not least, TCP. TCP is kind of an interesting situation. The idea behind NVMe TCP was to add in a fabric type, create the bindings that allow us to connect our NVMe into the TCP layer. But we can use the standard NICs that are available inside of hyperscaler environments, for example, where we have millions of them. Nobody wants to go back and retrofit a bunch of our NICs into those NICs. So what winds up happening is that you can then bind the NVMe transport into a traditional TCP layer. Now, why would you want to do that? Because wouldn't you necessarily have performance problems, especially with TCP? Remember when I was saying you don't necessarily want to oversubscribe your network, right? Well, the answer is because of the fact that for some types of applications, right, or use cases, latency isn't the actual problem. Data locality, data management, and data scale is the problem. But you want to necessarily remove some of the software layer of abstractions at the block level so that you can actually address the LBAs directly and quickly, and then have the upper layer management be effectively a software-defined storage solution. There are no features, there are no data protection features here. This is the raw command set that goes straight into the medium for NVMe, which means that everything that you would come to expect in an array or an appliance that would help protect the data has to be done somewhere else. Now, in really large systems, that is done somewhere else. That's naturally part of what a very large software-defined structure is supposed to be doing, which is why the hyperscalers are really interested in this technology. Right? But even they will tell you this is not for everybody. And I'm telling you this from myself and also from on the part of SNIA. Be careful about the fact that, hey, just like with iSCSI, I can use software initiators. This is going to be really, this is going to be really good. And truthfully, this will be very interesting once we start to get into additional discovery mechanisms which are required and the submission queue flow control specification, both of which are going to be finalized towards the end of this year. So NVMe TCP, submission queue flow control, and the discovery mechanisms are scheduled to be done around the end of this year. All three of those will do a really great job of being able to handle massively scalable NVMe TCP systems, but it doesn't absolve you of the responsibility of data protection, which is not part of the process.
But data protection isn't part of NVMe.
No, but think about where the responsibility and accountability falls depending upon which process. Like for example, in an appliance, they're first to tell you that they have highly available component systems, right? Yeah. In a SAN, you have multiple different ways of doing that. People tend to forget that when something new comes. All I'm saying is
Yeah.
don't think that that's going to change.
Yeah, and I'm just saying it was never part of the transport's responsibility anyway.
Right. And so I see the big red.
Okay. So since we're out of time,
Yeah, since we're out of time.
what's the state of multipath in NVMe over Fabrics?
Multipathing is called asymmetric namespace access. And it is, I believe it's finished. So I think it's going to be placed inside of the 1.4.
Okay.
Yeah, within a PCIe environment, multipathing was always possible, but was really kind of
Well, it
pointless.
didn't make any sense. You only have one bus anyway.
But what happened was there were actually new subsystems are coming out with multiple NVMe controllers, and being able to have that on a PCIe bus with multiple paths in it did start making sense.
Okay.
But so all that's going inside of the base spec because of that reason, but it obviously applies into the fabrics as well.
What do you think of a PCIe switch kind of fabric that exists, or a PCIe extenders, and how does that play out with NVMe over Fabric?
Well, it wouldn't be NVMe over Fabrics because we're essentially using the PCIe bus just in an extended format, right? So that would be only NVMe base, right? So that's where things get a little confusing for people because now I have a switch, now I have HBAs, but the reality is that we're not going to be using Fabrics. It's all going to be PCIe base. I'm sorry, NVMe base.
And you said the multipath was actually done?
I believe so, yeah.
Standards perspective?
Yeah. I think it.
For the next
spec.
for the upcoming version of the spec, not for
Right.
the current version of the spec.
I mean, it's passed the vote, it's passed the review, it's done, it's just waiting for the spec to be finished. If I remember correctly, I'd have to double check that to be sure.
And it's called multi-asymmetric namespaces?
Asymmetric namespace.
Close. It's asymmetric namespace access. So I like to highly recommend that you pay attention to some additional pieces of information where, obviously for 40 minutes I didn't have a lot of time to go into some of these specifics. The last time I did this presentation, it was 2 hours and I still ran out of time. However, we do have, at SNIA, we have tutorials on RDMA-based NVMe. We have tutorials on Fibre channel-based NVMe. The TCP stuff is still in the final works. So when that happens, we will be having webinars on the TCP-based stuff. One of the things that we're also working on is a series of networking impacts for different storage types. So there's a series of those coming on. I want to thank Diane, for example, because she is a goddess among women when it comes to coordinating this stuff, and she's hurting me as a cat for years. But we've got performance benchmarking webinars on Bright Talk. All of these things will help frame the conversation a little bit better, especially if you're a storage guy or gal. The idea is that you want to be able to find the information where you want, and SNIA has been doing a lot of work.
There was no discussion of InfiniBand, NVMe over Fabric over InfiniBand. That's been out there for a long time. The spec exists. Is that?
Well, NVMe over InfiniBand falls into the RDMA-based approach.
Oh, okay.
Yeah. So InfiniBand, Rocky v2, and iWarp all fall into the RDMA approach for what we were talking about.
Different versions of Rocky?
I'm sorry?
There are different versions of Rocky?
Yeah.
Yeah, so there's version Rocky 1 and Rocky v2. Rocky v2 is basically also known as routable Rocky. Effectively, Rocky v1 is a layer 2 protocol only, which requires just a flat L2 subnet. v2 is a similar approach. You still need to have lossless traffic at the L2, but you can route it using UDP.